Okay, so we have seen how the idea of a derivative is somewhat involved when we're working with a function of a complex variable, and we have seen how differentiability is a rather you know demanding condition upon a function. So in this lecture, we will look at what kind of properties must a function which is differentiable at a certain point, what kind of conditions must it satisfy, and which will allow us to derive the so-called Cauchy-Riemann conditions. Okay, so we start with this general form for a function of a complex variable. So we have f of z is equal to u of x comma y plus I times v of x comma y, where both u and v are in general independent functions of x comma y, right? So it turns out that you cannot have any arbitrary functions u and v if you want this function to be differentiable at some point, right? Even if u and v are extremely nice functions in functions of two variables. So you might think that basically the calculus of functions of a complex variable is really the calculus of functions of two variables, but it's not just that, right? So it's these u of x comma y and v of x comma y cannot be anything you wish. So let's see what conditions are satisfied by a function which has a derivative at some point z0, and what conditions must these u and v obey for such a function. So let's start with the definition of a derivative. So f prime of z0 is the limit delta z going to 0, f of z0 plus delta z minus f of z0, the whole thing divided by delta z. Now, well, this limit exists, so which means that it must be the same no matter in which direction you approach this point z0, right? So that's the core of the condition. So since you have all these infinitely many different directions, so demanding that this function this limit is the same in all these different directions will make these the real part and the imaginary part of this function, they have to obey some conditions, and these will be called the Cauchy-Riemann conditions. We will work them out. So let's see what happens if you take this limit, this general the limit is defined in a general way at this point. Suppose we take this limit along the real axis. So then we would have delta z is equal to delta x. So if we do this, then we have f prime of z is equal to limit delta x going to 0, and in place of z0 we put x0 plus I times y0 plus delta x, because delta z is delta x, minus f of z0 is the same as f of x0 plus I times y0, and then in the denominator we have in place of delta z we write delta x. So but we know that this function f of this whole stuff is the same as u of x0 plus delta x. You have the same argument, x0 plus delta x, so that's the real part, and then comma y0 plus I times v of the real part x0 plus delta x comma y0, minus I'm just expanding out this function and writing it in terms of u's and v's. So I have u of x0 comma y0 plus I times v of x0 comma y0. So the whole thing has to be divided by delta x, and so this is equal to u of x0 plus delta x comma y0 minus u of x0 comma y0, the whole thing divided by delta x, plus I times v of x0 plus delta x comma y0 minus v of x0 comma y0 divided by delta x. So now this is nothing but the partial derivative of of u and of v. Well, there's an I sitting here as well, because of you're taking this limit delta x, you're making a slight perturbation only along the x direction, right? So you have dou u by dou x, and in place of this, the second term is nothing but I times dou v by dou x. It's a partial derivative of this function v at x0 comma y0. Now let's see what would have happened if we had performed the same type of limiting operation but from a different direction. Let's take the y direction. Suppose we take delta z to be I times delta y. So there's no delta x, so it's just purely I times delta y. So then we would have, invoking the same definition, so f prime of z naught is equal to limit delta y going to 0, right? It's I times delta y going to 0, which is the same as delta y going to 0. F of, now in place of z naught plus delta z, I'll put x naught plus I times y naught plus I times delta y. Right? So z naught is of course just x naught plus I times y naught, but delta z is I times delta y. Then of course I have to subtract f of x naught plus I y naught. Now the whole thing has to be divided by I times delta y, because that's the small differential element. And then we write this as limit delta y going to 0 u of x naught plus, comma y naught plus delta y. Right, in place of the function f, I'm writing it as the real part and the imaginary part separately. So u of x naught comma y naught plus delta y plus I times v of x naught comma y naught plus delta y. So then we have to subtract out this function f of x naught plus I y naught, which I will also write it out explicitly as u of x naught comma y naught plus I times v of x naught comma y naught. The whole thing of course has to be divided throughout by I times delta y. So then again I separate out these two terms and write it in a suggestive form. So I have limit delta y going to 0 u of x naught comma y naught plus delta y minus u of x naught comma y naught divided by I times delta y plus I times v of x naught comma y naught plus delta y minus v of x naught comma y naught divided by I delta y. Now, well, I mean, it's convenient to put the second term first and the first term second. So now I have v of x naught comma y naught plus delta y. So the I has cancelled, and so we see that the first term is actually nothing but a small perturbation of delta y. You're asking what happens to the function v if you change delta y by the y coordinate by a small amount. So the difference divided by delta y. So it's like a partial derivative. And again, u also has the second, the first term has become the second term, and so we have a minus u of x naught comma, so this should be a minus I times, so there's an I sitting here. So, and indeed when I write the next step, so there is the I here. So it's dou v by dou y minus I times dou u by dou y. Okay. All of this has to be evaluated at the point x naught comma y naught. So the key point is that if you work out this derivative, right, according to first principles, by taking the limit along the x-axis, along the real axis, you get one answer. And if you work out the same derivative, by taking the limit along the imaginary axis, you got a different answer, right? So which is the only way to make sense of these two different answers is to demand that both these answers have to be the same, right? So your u and v have to be such that these two answers must be the same, and so that's what leads to the Cauchy-Riemann condition. So immediately it implies that dou u by dou x plus I times dou v by dou x must be equal to dou v by dou y minus I times dou u by dou y, right? So it's when two complex numbers are equal, the only way that can happen is if the real part and imaginary parts are both separately equal. So which means dou u by dou x must be equal to dou v by dou y, and dou u by dou y must be equal to minus dou v by dou x. So these two are the Cauchy-Riemann conditions. Whenever a function is differentiable at some point, then necessarily it must satisfy the Cauchy-Riemann conditions. So this is something that we could have actually obtained by taking a limit from an arbitrary direction. It's a little more involved, a little more messy in some sense, but let's look at what would have happened if we had taken some other direction other than y only x and y, right? We should expect the answer to be the same regardless of which direction you took it from. So let's verify that this two holds. Suppose we take this delta z to be delta epsilon times e to the I theta, right? So then we expand it out, we have delta epsilon times cos theta plus I times sin theta. Then if you take the derivative f prime of z naught, then you have limit delta epsilon going to 0, f of this more complicated argument now, x naught plus delta epsilon naught epsilon cos theta plus I y naught plus I times delta epsilon sine theta. So this just comes from a more complicated delta z minus, of course, just f of z naught, which is f of x naught plus I y naught, and in the denominator once again you have delta epsilon times e to the I theta. So I have expanded out e to the I theta in the denominator. Now we can separate these terms out, right? Conveniently we'll put, so first of all we'll write f in terms of u and v, and so I have, and then I will collect terms, so that u's appear in the first term and then v's appear in the second term, right? So I have merged a few steps, maybe a couple of steps into one, and so I have u of x naught plus delta epsilon cos theta comma y naught plus delta epsilon sine theta minus u of x naught comma y naught divided by this differential element, and then plus I times v of x naught. So there's a perturbation both in the x direction and in the y direction. So you have to consider v of x naught plus delta epsilon cos theta and comma y naught plus delta epsilon sine theta minus v of x naught y naught divided by delta epsilon times e to the I theta. So now we argue that, so this is nothing but the small perturbation of the arguments slightly away from x naught and slightly away from y naught, which is the same as saying dou u by dou x times dou epsilon cos theta plus dou u by dou y delta epsilon sine theta, and then there will be some higher order terms which anyway will go to 0 because you're going to be taking this limit delta epsilon. So we'll just keep the terms up to first order, and u of x naught y comma y naught anyway will cancel. So I'm just expanding. It's like a Taylor expansion of a function of a real variable, right? U and v are functions of real variables. So this is the usual kind of Taylor series expansion. So indeed I get only two terms here, and likewise this term involving which comes along with this I also yields only two terms, because this v of x naught comma y naught will cancel, and then the first order terms are all I'm keeping. Higher order terms in any case will go to 0 because you have only delta epsilon sitting in the denominator. Delta epsilon squared, of course, will just give you 0. So first order terms are all I have to keep, and delta epsilon cancels throughout. So I'm just left with, I collect terms in a suitable way here. I get dou u by dou x times cosine theta plus dou v by dou y times I sine theta. I have collected terms in a suggestive way, plus I times dou v by dou x cos theta minus I times dou u by dou y sine theta. The whole thing has to be divided by cos theta plus I sine theta. So what do we expect this quantity to be? We expect that this quantity to be independent of cos theta plus I sine theta. Right, so maybe there is a way to argue for this more rigorously, and maybe you can take like a derivative with respect to theta and show that the only way this quantity will be independent of theta. Right? It's just this is a function of a single variable theta. So definitely you can argue that if its derivative it has to be independent of theta, then its derivative with respect to theta must be 0, right? So, but you can also just directly just look at this equation and immediately convince yourself that the only way that this entire thing can become independent of theta is if you can pull out a factor of cos theta plus I sine theta from each of these terms. So the first term you can pull out a factor of cos theta plus I sine theta provided dou u by dou x is equal to dou v by dou y. So that's the only way this is going to happen. And likewise, if dou v by dou x is equal to minus dou u by dou y, you can pull it out, and then you will get a factor of cos theta plus I sine theta. So you need another plus sign here. So you need dou v by dou x to be equal to minus dou u by dou y, which is nothing but the Cauchy-Riemann conditions, right? So it is possible to argue, in general for considering an arbitrary direction, but it's easiest if you're working along the x direction and the y direction. That gives you the Cauchy-Riemann conditions in this in the standard Cartesian form, right? So these are the Cauchy-Riemann conditions, let's look at some examples of how this plays out. So, but before we do that, let's state the Cauchy-Riemann conditions a little more formally again, right? So, whenever a function f of z is differentiable at some point z0, then, well, Cauchy-Riemann conditions hold, which presupposes that these partial derivatives of u and v must exist at that point x0, y0, and they not only exist but they also satisfy the Cauchy-Riemann conditions. So they're connected in this inextricable way. So you cannot just take two arbitrary functions u of x, y and v of x, y and expect to just make one of them the imaginary part, the other the real part, and get a nice overall function for complex variable. You have to pick them up in such a way that dou u by dou x must be equal to dou v by dou y, and dou u by dou y must be equal to minus dou v by dou x. So let's look at a few examples to illustrate these ideas. So let's start with our favorite function f of z equal to z squared. We've already seen that this is differential every pair and its derivative is simply given by 2z. We already know this. So let's check the Cauchy-Riemann conditions for this function. So the real part and the imaginary parts for this function also we know. U of x, y is just x squared minus y squared, and v of x, y is 2xy. So dou u by dou x is definitely equal to dou v by dou y because both of them are equal to x here. And likewise, dou u by dou y is just minus 2y, and so is minus dou v by dou x. So minus 2y. So indeed, both the Cauchy-Riemann conditions hold. Okay, so not a surprise, is a function whose derivative is well defined, and therefore Cauchy-Riemann conditions hold at all points. So it's important to emphasize that the Cauchy-Riemann conditions are necessary conditions for differentiability, right? So what we have shown is that if a function is differentiable from first principles, then for sure Cauchy-Riemann conditions hold, right? So they're not quite the sufficient conditions, but they're almost but not quite. So we will come back to that point a little bit later. But because they are necessary conditions for differentiability, what it implies is if a function does not satisfy Cauchy-Riemann conditions at any point, then for sure it's not differentiable, right? So this is, if A implies B, then not B will imply not A, right? So if a function is differentiable, therefore Cauchy-Riemann conditions hold. There is the same as saying if the Cauchy-Riemann conditions don't hold, then it's not differentiable, right? So that's let's look at an example of how this plays out. Suppose we consider this function f of z equal to z star. We already looked at this and we saw how this function is not differentiable, right? So it is something that we could have, we could work out using Cauchy-Riemann conditions, because u of x, y here is equal to x and v of x, y equal to minus y, and immediately we can see that dou u by dou x is equal to 1, but dou v by dou y is minus 1. So there is no way that these two can be equal, and there is no point x, y for which these two will be equal. So therefore Cauchy-Riemann conditions are not satisfied at any point, and therefore indeed this function f of z is equal to z star is not differentiable, right? So this is a conclusion that we already arrived at using first principles, using the definition of the derivative. Let's look at one more example where we had difficulties when we were trying to take the derivative, which is the mod of this z squared function, which is just x squared plus y squared. So this corresponds to u of x, y is equal to x squared plus y squared, and the imaginary part is 0, right? So immediately we can see that dou u by dou x is 2x and dou v by dou y is 0. Dou u by dou y is 2y and dou v by dou x is 0 because v itself is 0. So we see that basically the Cauchy-Riemann conditions don't seem to hold except at one point, and that is the point when x equal to y equal to 0, which is the origin. If z is 0, then the Cauchy-Riemann conditions hold, right? So what we can say for sure is when the Cauchy-Riemann conditions don't hold, which is at every point other than the origin, for sure this function is not differentiable. Right? This is something that we already know. We have already come to this conclusion from first principles. But the fact that the Cauchy-Riemann conditions do hold at the origin does not immediately guarantee that it's going to be differentiable. But we have already seen that it is differentiable at the origin, and therefore it's indeed we do expect that Cauchy-Riemann conditions will hold as they do in this case. Right? It turns out that the requirement for the sufficient conditions for differentiability is a little more than Cauchy-Riemann conditions. So this is a somewhat of a technical and a subtle point, but we will have a short discussion about this as well. But in this lecture, we just want to point out that the necessary conditions, right? Which is that if a function is differentiable, then Cauchy-Riemann conditions hold, and this can often be used, to check for Cauchy-Riemann conditions and see if it does not hold, then for sure the function is not differentiable at a certain point. That's all for this lecture. Thank you.